In this video, we will see two approaches to statistics, the frequentist one and the Bayesian one. So, they differ in a lot of aspects. And the most important one is that the frequentists treat the randomness as objective and Bayesians treat it as subjective. Let me explain it to you. Imagine you have a coin and you toss it. What frequentists would say that with probability 1/2 it will end heads up, and with probability 1/2 it will end tails up, and you can do nothing about it. However, what Bayesian would say is that if someone knew initial velocity and all the initial parameters of the coin toss, he would be able to predict the outcome of an experiment, and for this person the experiment would not be random. Another difference between frequentists and Bayesians is how they treat parameters and the data. Frequentists would say that parameters are fixed and data is random, and they would want to find this optimal point. However, Bayesians would say in an opposite way, that parameters are random and the data is fixed. And it actually makes sense. When you train your model, you already know the data and it is not random anymore. However, there may be multiple good points, and you would like to define a probability distribution over them. Also, Bayesian methods work for arbitrary number of data points, while the frequentist ones work only when the number of data points is much bigger than the number of parameters. You may say that this is not a problem when we have the big data. However, you may remember that for neural network we have millions of parameters. However, the number of data points is only thousands. Another difference is how frequentists and Bayesians train their models. The frequentists train using maximum likelihood principle. That is, they try to find the parameters theta that maximize the likelihood, the probability of their data given parameters. However, what Bayesians would try to do is they would try to compute the posterior, the probability of the parameters given the data. And they will try to do this using the Bayes formula. And this will give us a lot of interesting aspects. If we computed the posterior distribution, in this case for the classification, that is the probability of parameters given the training dataset, the X train and Y train using the Bayes formula, we can compute the prediction, the probability of the new point Y test, given the training dataset. This can be done using marginalization principle. This will be the integral of the Y given X test and theta times the probability of theta given the training set. And we have estimated it using the training procedure. Bayes formula can also lead to regularization. We can treat the prior on theta as a regularizer. Imagine that you want to estimate the probability that your coin will land heads up. You already know that most of the coins land heads up with probability 0.5. And so you can use the following prior. That would say that most of the coins are fair. However, if you know that for your experiment the probability of heads can either be fair, that is 0.5, or biased towards heads, that is greater than 0.5, you could use, for example, the following prior. Also, Bayesian methods are really good for online learning. Imagine that you have data that comes in with some small portions. Then what you could do, you could use it to update your parameters and then use the new posterior as a prior to the next experiment. Let's see it closer. The new posterior, the probability of theta indexed by k, equals to the posterior that we get after observing data point xk. If we apply the Bayes formula, we'll see that as a prior we can use the probability of theta indexed by k minus 1. Let's see how it works on an example. Imagine you want to estimate some parameter theta, and here's your prior. Then you get, for example, 10 points, and you update it using the Bayes formula. And here's what you get. The variance of this distribution is much less, and also you see that the mean has changed. And as you get more and more points, for example here you can see for 20 points and 30 points, your estimation becomes more and more precise. And so you can predict the true value of the parameters very well. And now we've seen that there are a lot of advantages of Bayesian methods over frequency swarms, and we'll learn about them more throughout this course.